Welcome, ladies and gentlemen. Thank you very much for tuning in. I'm very pleased to welcome you all to our fourth webinar in the Rain Enhancement Hub series, hosted by the National Center of Meteorology and organized by the UAE Research Program for Rain Enhancement Science, UAE REP for short. My name is Yusuf Webby. I'm a program officer for the UAE REP, and I'll be moderating today's webinar. In our last three webinars, we've been demystifying the conceptual background of rainfall enhancement research and discussing the latest developments in the field and emerging challenges. We specifically discussed the UAE's efforts in both fundamental and applied research through both its operational cloud seeding program, as well as its cutting-edge research conducted by the UAE REP awarded projects. Currently, hygroscopic seeding, also known as warm cloud seeding, is being carried out operationally in the UAE, targeting liquid phase cloud droplets by activating their collision coalescence, or in other words, droplet-to-droplet harvesting and growth into big enough raindrops that can fall through their cloud bases. However, recent findings from our UAE REP projects suggest that mixed phase clouds in the UAE generate enough ice particles in their upper levels, which can be susceptible to an alternative approach of seeding, which is known as glaciogenic or cold cloud seeding. Joining me today to learn more about glaciogenic seeding, its programmatic management, its long-term assessment is Dr. Mohammed Mahmoud, Director of the Climate and Water Program at the Middle East Institute in Washington, D.C. One of many of Mohammed's professional accomplishments includes negotiating and formalizing a 10-year multi-state weather modification funding agreement between 7 Colorado River Basin states. We're very fortunate to have him with us today to present on this project. Audience, please go ahead and type in your questions at any time during the webinar using the chat box. We'll be sure to address your questions during the Q&A session after the presentation. I'll now hand over to our guest speaker, Dr. Mohammed, to give his presentation.
Great. Thank you, Yusuf, for that very kind introduction. I really appreciate that. And happy to present on this topic. I think it's very timely, and that there's a lot to discuss in this area. Of course, the differences in warm weather versus cold weather, the idea of how do you implement a large programmatic agreement amongst different states and entities, and then what are some of the issues that come up for cold weather cloud seeding, as well as just in general cloud seeding issues when you have such a wide type of program. So today I'm going to be focusing on work that I'd previously done in the past on the area of the western United States on the Colorado River Basin, which is a very significant basin in the United States, and talk about some of the issues there in terms of water supply needs and water supply management, and then why cloud seeding was an important tool as part of that scheme. So this is just a visual of the Colorado River to start. But let's dive into the Colorado River Basin itself. So what you see on the left-hand side, and I apologize if you can't see it very clearly, but I'll walk you through the graphic. This is the Colorado River Basin. It touches 7 U.S. states. And also at the tail end of the system, you don't really see it here because it's cut off at the US border, but the system itself actually, the river itself actually also flows into the country of Mexico from the United States at the end of the system. The basin itself is split into 2. We refer to as the lower basin, which is where I used to work and represent, which includes the states of California, Nevada, and Arizona. And generally speaking, that's where a lot of the water consumptive use is taking place in the lower basin. Everyone's familiar with California. It's a very large state in terms of number of people residing as well as consumptive use. And then you have the upper basin states, which comprise New Mexico, Colorado, Wyoming, and Utah. And when we think of this river system, it is a snowpack driven system, meaning the water supply is primarily generated from the amount of snow that is developed over the winter months. and a lot of the flow is then generated during the snowmelt season, which occurs in late spring, early summer, usually between the months of April and July. And most of that, as I said, that snowpack develops in the upper basin. So a lot of the health of the system is really dependent on how much snow is received, primarily in Colorado, Wyoming, and Utah. And there are a couple of reservoirs in there that help manage the system. And so this graphic is actually from the United States Bureau of Reclamation. And the Bureau of Reclamation actually manages and operates two key reservoirs that help balance the water contents of the system, certainly between the upper basin states and the lower basin states where most of the water use occurs. One of those significant reservoirs that you may have heard of and seen in the news is Lake Mead, which is situated just outside of the city of Las Vegas. And what you may have been seeing in the news is reports of being a water shortage on the Colorado River and how Lake Mead has been declining rapidly. In fact, on the right-hand side of the slide, you'll see a couple of graphics, the first of which is the monthly elevation of Lake Mead at Hoover Dam. That's the dam that's associated with the reservoir of Lake Mead. And you can see the monthly elevations steadily declining overall from the year 2000 essentially to the present day. Now, why is that important? Just from a perspective of just a declining reservoir is not necessarily a good thing, but also the fact that declines in the elevations of Lake Mead actually translate to important water operation issues, primarily for the lower basin, since this reservoir is situated in the lower basin and behaves as a storage for the lower basin uses. As Lake Mead steadily declines and reaches particular elevations, these elevations then trigger what we call essentially tiers of shortage. And under successive tiers of shortage, there are three primary ones. The water that is then released from Lake Mead to the three lower basin states and subsequently the Republic of Mexico declines significantly. Each of the states have a particular allocation to the river, and in the case of the lower basin, those allocations begin to decline, and there's a prescribed amount. So I won't go into detail just for brevity for the rest of the talk. But that has serious implications for mostly Arizona as well as Nevada, and then now California under a set of agreements that they now also may suffer a shortage under successive tiers. The big takeaway is this is happening right now, and this is what you've been seeing in the news. The lower visual shows you the reservoir of Lake Mead, a little bit north of Hoover Dam. And it's showing you how the reservoir has declined in terms of storage from 2000 to 2021, last year. This year was the first year that a shortage has been essentially declared. The declaration happened last year for Lake Mead. And this year, Arizona and Nevada are operating under shortage guidelines. What is also being indicated from early projections is that we may, those of us that reside in the lower basin, me being one of them, experience the second tier of shortage as soon as next year. So things are rapidly declining in terms of hydrology. Now the question is, why is this relevant for what we're talking today about cloud seeding and weather modification? Well, the reason being is that one of the things that were implemented as part of the Colorado River Basin's response to essentially climate change and the large long-reaching drought it's been under for the better part of 2 decades, is cloud seeding was explored in the upper basin states of Utah, Wyoming, and Colorado as a tool or mechanism to try to mitigate against this long-term drought. And as I mentioned up front, this is a winter cloud seeding programs. And so all three of those states have had very active and robust cloud seeding programs that have spanned a number of years in each of their respective cases that are meant to mitigate against or provide another water augmentation source. So I'm going to walk through these three different states programs to give you a flavor of how they do it and what their targets are in terms of seeding. So the first one, and this program will come up later for a different reason, is the Wyoming program. And their winter cloud seeding activities are actually focused on a number of ranges. And I'll talk about later why winter cloud seeding tends to take place in proximity to mountain ranges. There's a physical issue that assists in that. So the winter cloud seeding program in Wyoming has really spanned a number of years. Started in the research side from 2004, continuing onwards, where there were a number of feasibility studies. One you'll see up on the left side of the visual, the map, is the Wind River Range, and that range actually, the accumulation of snowpack there and subsequent melt actually feeds into the Colorado River Basin itself. And then there are a number of other seeding sites along the states. The Sierra Madre and Medicine Bows are going to be, I'm going to mention them later for another important reason. There's the Laramie Mountain Range and the Bighorn Mountain Range. And there's been a number of feasibility studies associated with these sites and respective programs within the state of Wyoming in terms of siting, ground-based generators, which I'll talk about a little bit later. That's how we're able to seed these areas and adjacent to these mountain ranges. And then the operations, and primarily they have been, up until quite recently, ground-based generator type programs, ground-based seeding. In the last few years, there's been implementation of an aerial program, which is now seeding clouds via aircrafts, releasing the flares via aircrafts into the clouds as opposed to from the ground. But we'll talk a little bit more about the Wyoming program later in terms of efficacy of cloud seeding. But this is just an idea of their program and the areas which are being seeded within that state. Next, we have the Colorado program. And Colorado program is really significant in the sense that when we think of the upper basin and the amount of water that's contributed to the main river of the Colorado River from the various tributaries and streams in the upper basin, the significant amount of water is being contributed from the tributaries associated in the state of Colorado. So this is a very important program in terms of potential for enhancement of spring and summer snowmelt and runoff. And as you can see, the interesting thing about the state of Colorado, just to share just the geophysical aspect, is that the state itself really straddles both in and outside of the basin itself. Some of you may be familiar with the city of Denver, the Mile High City. It's a very high elevation location. But as you can see, the colored areas in the map indicate the locations where there's generators, and those green dots are the ground-based generators that are sited in these various locations that are targeted for seeding. But you'll see really almost half of the right side of the state does not reside in the basin. So a lot of the activity occurs on the western slope. So even though Denver receives a lot of Colorado River water, or a significant amount for the state's allocation, it's an out of basin diversion. But anyhow, the focus really here is that a lot of the activity here is occurring on the western portion of the state. That's where these, and you see a number of generators are sited. Grand Junction area is a significant one. We visited that a number of times in our site visits as part of a larger group visiting the Colorado programs. It's a very robust program. And also one of the things about this program is it doesn't just receive funding from within the state mechanism and then from the basin states. I'll talk about that programmatic funding agreement, but also they get a lot of cooperation with ski resorts. You know, Colorado is known to be a very active ski industry locale. And so a lot of the ski resorts also participate in terms of helping site the generators within their areas, and in some cases also co-funding the program. As you can imagine, it's beneficial to them because from a business perspective, you're helping them create more snow in the location they exist. And then finally, in terms of the primary programs, the Utah program is also a very important program that's part of the upper basin set of weather modification programs. And I may have failed to manage who manages each of these programs. In this case, for Utah, it's the Utah Division of Water Resources. As you can see from the map, there's a number of locations, and the dots, again, in this case, the black dots indicate the ground-based cloud seeding generators. And there's quite a number of them on the various areas and regions that have been seeded throughout the year. Some have not been necessarily seeded continuously, maybe intermittently, but all of these programs have contributed throughout the lifespan of the Utah program in terms of generating snow. And most of these essentially, they do feed into the Colorado River basin. I think the two areas just to highlight that I think are probably the most significant, potentially productive in terms of snowpack that contribute to the basin are on the brown areas on the top right, which are the Uintas. Those mountainous regions are also very important for this program in terms of contribution to the snowpack that later translates into runoff. So I mentioned this programmatic agreement, and Yusuf also mentioned in his introductory comments. So up until a few years ago, a lot of these three programs were, for the most part, let's just say, operating independently, meaning that each program was tasked with, through their own internal mechanisms, develop the funding needed to operate their various seeding programs in their respective states. A lot of it was tied with state funding, certainly for most of it. Others, like in the case of Colorado, was able to receive funding from outside sources like ski resorts. Wyoming, now recently in the last few years, have received from mining companies. And then each of them were also partnering with entities from the three lower basin states, Arizona, Nevada, California, to help supplement their funding, because the lower basin states recognize that in drought and in now active shortage, but leading to the potential of active shortage, any opportunity to augment the water of the system is really important. And so that recognition occurred early. And so each of those programs had an arrangement with each of the lower basin entities. And we operated in this way for a number of years. It wasn't until I think around 2018 that we recognized it may be better for us to kind of pool our efforts and operate as a collective, meaning that instead of each of the lower basin states entities that fund these three programs and the offices that manage these three programs in the upper basin can actually co-fund them together under a large basin-wide agreement. And it's really became beneficial in a number of ways. It mainstreamed the process. It brought all of us together in the basin from a technical standpoint, as well as from an operations standpoint, to better collaborate, coordinate our efforts, and understand what's happening in each of the states, as well as the funding that is received, and allowing sort of more of a dynamic input in what actually occurs year to year in those upper basin states in terms of where are these programs seeding, are there any enhancements we can do, inputting of or installment of new generators, exploring potential research or feasibility applications that can help enhance each program's ability to contribute more stream flow by generating more snow. So 7 is essentially entities, and one other added benefit is this also brought the state of New Mexico, the representatives from the state of New Mexico in this effort, in this umbrella. Prior to this, the state of New Mexico were providing funding to a particular program in the state of Colorado. So they were kind of adjacent in terms of all these individual one-to-one efforts with the upper basin, lower basin entities. This brought the state of New Mexico also together, and I think that that's a great additive in terms of interbasin collaboration. So as I mentioned, this was we developed a programmatic agreement, which I was the representative for the Arizona agency that was involved in this effort and led that development process for the agreement. And here's just some key aspects of that agreement. So it was executed by 2018 by essentially the executing authority from each of those seven entities, the programs, and then the funders. And one of the things that was agreed to in terms of funding was that for each of the three primary funders from the lower basin, those organizations would each provide up to $500,000 annually collectively for all approved upper basin activities. New Mexico's entity, New Mexico funding partner there, would continue to offer $20,000 annually for the activities, and essentially that was primarily directed to that activity or program in the state of Colorado. And then internally for the agencies in Wyoming, Colorado, and Utah, they'll continue to provide matching funds, approximately matching funds from their internal funding mechanisms within their state. We left room for other funders to continue to fund outside of the lower basin, upper basin partners. I mentioned skiers such as the ski resorts in California, potential power providers, mining companies, etc., just to help offset the cost burden. And one of the other interesting things I think is very useful is through this program or programmatic agreement, this creation of a technical committee that had a representative from each of those seven basin state agencies. And what the technical committee did was they met at a minimum once on an annual basis in the early summer to do a couple of things. One, to review the proposals put forth by each of the upper basin programs in terms of what they wanted to do in terms of their cloud seeding efforts for the upcoming water year. And the water year essentially operates from October to September. And so we meet in early summer. Every upper basin program presents on what their proposed set of activities for modification in the basin will be for the upcoming water year. We have a discussion, clarify any questions that may have been asked. The funding programs get together, discuss, okay, are we in support? Is there some feedback we need to get back? Should we adjust some of the applications that are being proposed? And then through feedback with each of the programs, there's a dialogue that goes back and forth until we finalize what those activities for that year is. Another thing that occurs through that technical committee, there's a lead that helps to coordinate the technical committee activities. And then for these annual set of activities, have another set of executing signatures from each of the signatory authorities of each of these entities that then says, great, we all agree on the activities for this upcoming water year. Let's go forth and move on that. And that's primarily then shifted back to the upper basin entities and their respective programs in their respective states. And so the other piece that just is also in there, the final piece, is that there's always an annual reporting mechanism. So at the conclusion of each water year, the upper basin states will then prepare a short report on what happened for that particular year in terms of the funding expended, in terms of the activities done and efforts, what areas in their state were seeded, how often, etc. So more of the minutiae in terms of what actually occurred. And that helps inform us in subsequent water years when we have discussions on proposals for new activities and what should be funded, what shouldn't, where do we amend the activities and so forth. So it's a very dynamic group, and just on a personal level, it's a group that's worked together for many years. The weather modification group in the Western United States, very tight-knit, certainly those on the Colorado River Basin. So you build great relationships, and these great relationships then also enhance these types of collaborative efforts. I would argue these relationships didn't exist, we may not have been able to develop this type of agreement. So that's really a testament to the personnel involved in this. I mentioned the Wyoming program at the front end, and I just want to revisit it again because one of the things it did that I thought was just immensely useful for weather modification activities in general, really, for winter cloud seeding, is the pilot program it ran initially. And the reason I bring this up is it answered a very important question that always pops up when people talk about cloud seeding is what is the efficacy of cloud seeding? How do you know by seeding these clouds during winter that you're able to produce snowpack that then can translate into water supply? So what the Wyoming program did in its early run is I'd mentioned the Wind River Range as the primary mountain range that feeds into the Colorado River Basin. But then there are these two mountain ranges on the other portion of the state, the Sierra Madre and the Medicine Bows. What they did for a number of years, they conducted a randomized seeding experiment, the goal of which is to answer this efficacy question on cloud seeding enhancing winter precipitation. Essentially what they did over those two periods, when the conditions were ripe and suitable, essentially for both mountain ranges to be seeded, and these were also ground generator based seeding locales, once conditions were appropriate for both mountain ranges, and that included primarily three things, which is the mountaintop temperature was colder than negative 8 degrees Celsius. I'll talk about later why that's an important number. Wind direction would transport the material that is released from those generators, in this case being silver iodide, and we'll talk a little bit about why silver iodide is the material used, into the targeted clouds, and then the presence of what we refer to as supercooled liquid water, which is what is essential for droplet formation. That's the moisture in the atmosphere that then can translate into water vapor droplets and then precipitation. So what they did is, when these conditions existed essentially for both mountain ranges, they decided to randomly select which of those two mountain ranges would be seeded. And they conducted this for every storm event or seeding event that met these physical conditions to be seeded. And these occur multiple times over a season for a number of years. And what they ended up finding out as they collected all of this data over a number of years is they were then able to determine, based on this randomized seeding, one mountain range versus the other, on really how effective the cloud seeding was, at least initially in terms of the enhancement to the snowpack. And what you see on the graph is pulled from their report, which is a really wonderful report, is essentially from the primary analysis, and they had to do some corrections or adjustments in terms of how they conducted the analysis, which then ultimately led to the final conclusions. So initially, without data correction, they were able to see there is some positive net effect of cloud seeding. In this case, there was 3% increase in precipitation. But then they realized, as they dug a little bit deeper into data, they had to make some data corrections that then impacted that potential percent increase in precipitation and ultimately the amount of snowpack that was accumulated. One was they needed to correct or adjust for the occurrence of unintended downwind effects. So specifically in this case, because of the locations of the mountain ranges somewhat adjacent to each other, they're not exactly next to each other, is that depending on the storm track and the storm path, if Sierra Madre was seeded, there were incidences where there was carryover effect of that storm and wind, such that if the Sierra Madre was seeded, some of that precipitation or impact that was supposed to target Sierra Madre sort of overflowed or overlapped in an unintended fashion to the Medicine Bow mountain range. So they had to go back to data and correct and extract those out from those data points from being viable in terms of the final efficacy number. And then the other adjustment that was conducted was that there was really a target number of generator hours, these are ground-based generators, that had to be operating sufficiently with the amount of silver iodide available to truly seed these seeding events, clouds, storms, etc., appropriately. And they found that there were some incidences where there were low generator hours, meaning there was an insufficient amount of generator hours that didn't seed those particular storms effectively. And so they had to adjust for that or course correct or correct those entry points as far as data. Ultimately, and then there was also a modeling aspect that was also implemented to help add another data point in terms of efficacy. Ultimately, with these adjustments, and I also can't go into too much detail with the time we have, what they ultimately found out is from that 3%, without the data and analysis correction, which by itself illustrates a positive outcome in terms of efficacy, is actually, with these corrections, the assessed seeding effect actually ranged between 5 to 15%. So it may seem modest in terms of numbers, but you also have to recognize in terms of expenditure as a water augmentation strategy, cloud seeding still is, in some cases, 1 to 2 orders of magnitude cheaper than some of the more traditional sources of water augmentation. And the one that I'm sure is familiar in the Middle East region is desalination. Is significantly orders of magnitude, at least 1 to 2, at least 1 order of magnitude cheaper than desalination. So the number may seem modest, but actually translates to a cost-effective approach. So let's talk about winter cloud seeding and how it may be different from warm weather cloud seeding that you all may be familiar with in the Middle East region. So I kind of hinted on this earlier when I talked about the Wyoming program. And for winter cloud seeding to really truly be effective, there are a number of conditions that have to be met. And these are primarily meteorological conditions. I'm sure audience will appreciate that, that are more meteorologically inclined. One is the coverage in terms of where you are seeding. For the most part, these programs utilize ground-based generators, and they are situated close to mountain ranges. And I'll talk about a little bit more why that is. But the primary reason is, before seeding anything, meteorology is an important aspect of any seeding programs because there are meteorologists associated with these programs that track the conditions that I'm going to talk about now, as well as the track of potential storms and clouds that are viable for seeding in terms of them producing precipitation downwind or in the track of the movement of the air. So the targeted clouds must have at least forecasted to persist long enough that they will actually able to produce precipitation and adequate seeding to take place. So enough of a persistence of time of that cloud so you can seed it effectively, and also for it to precipitate adequately the amount of precipitation that is viable out of it. Temperature is important. I'd mentioned -8 degrees Celsius as being a minimum target temperature. Has to be less than that to seed. And the really primary reason of that is its condition to the seeding agent. In this case, what's being used here is silver iodide. It reacts much more effectively under these colder temperatures, not so much with warm temperatures. So having cloud temperatures of less than -8 degrees is ideal. And then wind, and that sort of connected to coverage, which is the forecasted trajectory of these storms. And they're orographic storms because they pass and develop more fully over mountain ranges as the clouds pass over mountain ranges. So the path of the wind, path of the storm has to go over the mountain range that is an intended target, because that's also where the cloud seeding generators are placed, on one side of the mountain range. And I'll talk about why that is here in a minute. And so that is also important. And then finally, moisture. You can't seed if you don't have enough moisture in the atmosphere. And in this case, we'll refer to as moisture is really super cooled liquid water. That's the ideal type of water vapor or liquid water that then is able to precipitate more effectively under cloud seeding implementation. So here's just a graphic from North American Weather Modification Council. I'll mention them in the end. That really illustrates how winter cloud seeding or the snow augmentation process occurs. And like, as I mentioned, for winter cloud seeding, at least in the areas in the basin, it's very critical to have generators and mountain ranges situated. So in this case, you have airflow moving across the mountain. You'll see the numbers 1, 2, 3, 4. I'll just briefly walk you through it. You have a cloud seeding generator situated along the side of the mountain range, and that's where you see point 2. And what happens is, if the conditions are ripe, you have a storm track, you have the path of the air moving across the mountain range. Meteorologists will flag the operators and say, hey, these are the hours or time frame which the conditions are going to be perfect. This is probably when you want to operate. The operators then turn on the generators, and some of these, old school is, go and manually turn them on, but now we have remote-based generators, so they can be turned on. The operators don't have to be on site. And then they release these flares. The silver iodide is released up into the atmosphere in flares. They interact with the airflow movement such that when that airflow ascends over the mountain range, and primarily as it starts to descend from the mountain range, as you can imagine, as air rises up, it condenses. That's what sort of helps this placement of the generators. You're now targeting areas of condensed air, and if conditions are right, which they should be to seed, sufficient supercooled liquid water. And then as the air descends or begins its descent on the other side of the mountain, then you start to see the precipitation effect occur. And what's happening in the atmosphere is the reaction, and I'll talk about that, is how the silver iodide reacts in the clouds to produce more precipitation. So essentially, this is the reason why these generators are placed on mountainsides in terms of generating more snowpack during winter for these types of programs. So how does this work? It's primarily through ice nucleation. And what the silver iodide does is, as it's introduced into the cloud, it behaves as a cloud condensation nuclei. So it acts as a source of particles where water vapor naturally, or is inclined, I should say, to condense and coalesce around. You can see the graphic here. As it condenses, the water vapor then grows in size for the cloud droplet, and through further condensation within the cloud, these large cloud droplets then reach a size where they're then able to escape this reaction within the cloud and to come out as precipitation, in this case being snow. Another question that's always generally asked is, well, what are the issues of doing this? Are you reducing the amount of water or rain that someone else will receive downstream because you're doing this cloud seeding at some area of track prior? And I think what a lot of people fail to recognize is there is a lot of atmospheric water vapor, and we're only enhancing a small amount of it, meaning that, yes, there is a finite amount of water vapor in the atmosphere, but it's such a large amount that this adjustment doesn't lead to this effect of robbing someone from water because we're seeding one area versus one later downwind of the track of the storm. So just the visual on the right, just to give you some numbers, there's only about 20% of moist air or water vapor in the atmosphere actually condenses. In this case, when we talk about these mountain ranges for winter seeding, only about 20% of moist air condenses as it cools down from being forced upward over the mountain range. So meaning as it starts to descend on the other side. So only 20% of that water vapor that's in that region actually is then translated to condensed cloud water. When we think of seeding, and not even seeding, actually, the winter storms, out of that 20% of condensed cloud water that's in the atmosphere within these clouds, only about 30% of them can be efficiently converted into precipitation by winter storms. So when you think of that in terms of the 100% of atmospheric water vapor in that particular region, that's only about 6% of water vapor. So this notion of affecting the potential precipitation in one area versus the other because of cloud seeding is actually erroneous. And to add to that, cloud seeding at its best only enhances that precipitation by about 0.9%, right? So as I mentioned, it's a modest enhancement, but is an effective one. It's a science that works. And so there is still much more water vapor in the atmosphere that could then translate into precipitation. I think the main takeaway here in terms of the process of ice nucleation and winter cloud seeding is the effort only truly enhances the amount of precipitation that's going to happen, not necessarily adjust the distribution of rainfall, only enhances that particular distribution that would have naturally occurred because of storm. We can't control the weather. We're only encouraging these clouds to produce more precipitation along its natural path. So I mentioned silver iodide as a material. So let's talk a little bit about how this works. Most of these programs, essentially all of them really, utilize ground-based generators. And as mentioned, Wyoming has recently looked into aircraft generators, aircraft seeding as well. Silver iodide is the ideal and preferred method because of how effective it works in these colder temperatures, much colder temperatures in these upper basin states, less than -8 degrees Celsius. And the silver iodide is released by burning flares, and like I said, acts as cloud condensation nuclei. The other question that's being asked is how much silver iodide is going into the atmosphere through these applications, and how dangerous is it? Well, part of that question I'll answer in a little bit, but only about 2 to 3 kilograms of silver iodide is released per generator in a season. The other thing you need to consider is that a lot of these generators, you can see in that graphic on the right, the photo on the right, they're in very remote locations because they tend to be higher elevation to be effective, along these mountainous regions. So not a lot of material is used, and most of the material, almost all of it really, reacts in the upper atmosphere. That's part of the process that has to happen to produce winter precipitation. And in fact, these programs wouldn't be seeding if the conditions weren't right, as we talked about a few slides ago, to completely react this seeding material in order to create the precipitation. It would be poor application to seed clouds that weren't going to, or conditions that weren't going to produce precipitation. So the meteorology is a very important aspect of these programs again. So I'll touch this a little bit further on this extra area effects, right? This crude notion of robbing Peter to pay Paul, which is the idea of you're seeding one site. That means some site downwind of where the storm track was going to move is going to lose that precipitation. So I answered part of that question when we talked about the water vapor in the atmosphere. But let's talk about actual studies that looked into this. So there's a number of studies, a little bit dated, but Hunter 2009 article looked at a number of studies. So it was a comprehensive literature review on the potential of extra area precipitation effects, meaning are these programs reducing the amount of precipitation that otherwise could have occurred downwind, or maybe potentially increased it? And what this paper did is assessed multiple cloud seeding studies, greater than 28 in number, and the extent of seeding effects beyond the specific target areas. So as we looked at the different upper basin programs, there are actually target areas that are meant to be seeded, and they looked at further than these target areas to see what are downwind effects, and up to 250 miles away in some cases. What they found is that there was evidence of actually positive seeding effects beyond the target area, meaning no decrease in precipitation downwind or further out from the target area, meaning no one was negatively impacted by having reduced precipitation. In fact, quite the opposite. Shouldn't be a surprise based on what I'd mentioned earlier, is increasing the actual precipitation. Now, there is recognition that these types of extra area effects are actually impacted by a number of things that are a few really quite outside of our control, which is what's the local climatology of that particular region. And you have to recognize we cannot control the weather, and the weather, as we all know, can be quite unpredictable, meaning there's a certain level of uncertainty in terms of natural precipitation distribution, how a storm behaves. For example, meteorologists may flag a particular storm as perfect for seeding and as forecasted and looked ahead to say that a particular storm will persist for a number of hours and the perfect seeding conditions will persist for a number of hours. But then things happen and these storms abruptly change in an unexpected fashion. This is the reality of this particular business. We can't control the weather. We try to forecast as best as we can, but conditions change sometimes unexpectedly in real time. So you have to really factor that in. So that could play a role in extra area effects. And then obviously level of seeding operations. We talked about insufficient generator hours as one of the adjustments that had to happen in the analysis in the Wyoming program. So on the flip side, some programs incorporate what we refer to as suspension criteria. So we looked at what if not enough precipitation is occurring downwind. It's a reduction, and we've essentially answered that as being erroneous. I think the other aspect is, what if you produce more precipitation than intended just because of these unintended climatological effects? Many programs, especially because they're winter programs, incorporate suspension criteria, meaning that depending on the amount of snow water equivalent, or SWE, which is essentially the accumulation of a snowpack in a particular region, they have a particular threshold that says, hey, if we're tracking the snowpack conditions and exceeds a particular depth or volume, primarily depth in the case of SWE, inches or feet, they will not seed. They will halt the programs or in that region to seed until the SWE is maybe lower than that particular threshold. You may ask, why is that the case? Well, it's more of a security and protection aspect. There is concern if there is excessive amount of SWE that you could lead to potential flooding events, or depending on the location, potential for avalanches, etc. So more of a security and safety aspect to minimize maybe potential of flooding during the snowmelt portion, because there's too much SWE or snow that's accumulated and expected. So some programs do have that built in. And then one other aspect to discuss is environmental concerns. When I say silver iodide, people almost exclusively focus on silver. It's a metal, it's potentially toxic, you're releasing it to the atmosphere. This is not a good thing. Well, silver is different than silver iodide. And there are a number of studies that support this notion that use of silver iodide is safe and appropriate, really. And one of these is looking at the background levels of silver itself that naturally occur in environments, and in this case, being in parts per billion. Surface waters, remember this is supposed to be a water augmentation strategy, have a range of 0.2 to 2 parts per billion of silver in the atmosphere, or in environments, I should say. And the Environmental Protection Agency in the United States has specified that the drinking water standard for silver is 100 parts per billion. A number of studies that looked at this question actually determined that the silver concentrations that occur in seeding areas tend to be even well below the EPA standard. So here's some examples to share with you. In the Sierra Nevada mountains, there were 2 sites where post-seeding, the amount of silver that was found was 0.02 to 0.4 parts per billion versus 0.02 parts per billion, which is the background or environmental amount. So still really a negligible amount of silver added, if that's even the case, because it's comparable to 0.02 background versus 0.02 post-seeding. Another study by Cooper and Jolly, some of these are a little bit dated. I'm sure they're more recent studies, but just to really illustrate the numbers, silver and snow in a seeded versus unseeded storm. And the unseeded storm, it's 0 to 0.02 parts per billion. And after a cloud seeding event, 0.01 to 4.5 parts per billion. So minimal in terms of addition, and at the extreme end, still very much below the EPA drinking standard. And then the last one, San Juan Mountains in Mexico, 3-year study, they ultimately found no significant increase in silver levels. And this is truly by design, because the idea is you want to introduce material that actually sufficiently reacts to produce more precipitation. And those conditions, as I mentioned, are carefully tracked. And then finally, EPA exposure and risk assessment for silver. EPA determined that cloud seeding is not expected to contribute significant amounts of silver to water from precipitation. Now, some may ask, well, what's the cumulative effect? We're looking at particular seeding events, and through time, what's the cumulative effect? Well, remember, this is in a static environment. These regions that are being seeded, the snow that's being produced, the precipitation continues to go downstream. So season to season, these amounts of water are essentially displaced downstream. And where are they displaced? Well, they move into other states and regions and are then diverted, extracted for use. And for drinking water, any water that's diverted or taken out of the river for at least human consumption and drinking water standard is always treated. So there are still levels of protection, even if you're not convinced from these studies that there is really a negligible amount of silver added, if at all, in the case because of cloud seeding. And this is my last slide, and I think we can go into questions after this. I mentioned the North American Weather Modification Council. So we talked about the technical committee from the Colorado River Basin as a collaborative effort in terms of funding and operating the programs. This is an alternative mechanism of bringing folks together to work on cloud seeding and weather modification issue. And this is a broader range than the Colorado River Basin, truly the Western United States. So it includes Texas and North Dakota and Idaho as well. And this is a group that meets twice a year, and really their focus is to learn, promote, and educate in terms of research related to cloud seeding. Each of these programs, even those outside of the Colorado Basin, have very robust programs, including both aerial and ground-based seeding. In some cases, some also have warm seeding, in the case of the state of Texas. So another tight-knit group that's built strong relationships in terms of sharing of knowledge, information, application, and looking at more than just cloud seeding for water supply. Looking at effects or applications such as mitigating fog, suppressing hail to reduce potential damage from those types of storm events, and ultimately to advance research, development, and application of weather modification as a science and approach that's really been around for a long time. And I was fortunate enough at one point to serve as their president. And it's really a very special group of people that really do their best to advance the state and science and collaborative efforts in terms of weather modification. So I think with that, that concludes my slides proper, and I'm happy to address any questions.
Well, thank you very much for the great presentation, Dr. Mohammed. We learned a lot from the lessons you shared from the Colorado Basin project. We do have a few questions which we can hopefully tackle now for the next 10 or 15 minutes. I know it's early morning for you, and thanks again for making the time to join us. So the first one is, so based on your experience with the Colorado project, it's of course a multi-state weather modification project, how would you recommend a similar GCC-wide cooperation for these activities for the region? What kind of challenges do you envision, and some of the potential solutions?
That's a great question. I think my suggestion would be, and it's recognition of the fact that what's happening in the GCC in terms of cloud seeding efforts is a little bit different than what's happening on the Colorado River Basin. Recognize that in the case of the GCC, it's essentially warm weather cloud seeding. And then the issues are a little bit different in terms of the programs. And I would say, maybe respectfully, the programs are, in terms of age, maybe are still pre-adolescent, right? They're still budding and growing programs. So there's a lot of opportunity for growth and enhancement of those programs. I think the model that I would probably recommend would be somewhat of a hybrid or in between what was done on the Colorado River Basin Technical Group or Committee and the North American Weather Modification Council. The driver for, not necessarily the driver, but the biggest driver for that cooperative basin-wide programmatic approach was really driven by funding, which is how to maintain a consistent source of funding for all these programs for a large amount of years. I may have failed to mention this, as the agreement essentially is in effect to 2026. So quite a number of years as a somewhat guaranteed source of funding. I suspect that may not be the primary issue for the GCC countries in terms of developing those financial resources, but I think something that is closer to the North American weather modification framework is suitable, because I think since the programs have much more room to grow and to mainstream in the region, it could serve a collection of researchers and operators and programs in the region could work together, not just to enhance existing programs, but to look at feasibility and viability of adding new programs in other countries where cloud seeding is potentially viable. So I think the framework that's probably more applicable is one that looks at added feasibility of how can we expand existing cloud seeding in the region, while also, I think to a smaller degree, for those programs that do exist, such as in the case of the UAE, how do we enhance what we have? And that's more of a technical question. I think the cooperative piece of how do we expand cloud seeding becomes more of a viability, feasibility, and then also a way to build the partnerships. I think one of, I may have mentioned it, but I still feel continues to be understated, is how important these relationships are the interpersonal relationship between the entities within these states to push forward these efforts. We talk about negotiating agreements and operating programs and collaboration between states. We say it in a way that seems just matter of fact. There's a lot of human capital that is a part of that effort, and it truly is a testament to great working relationships. And no, it's the soft side of things, but it's also quite important.
No, indeed, and you really set the pace for all that cooperation you've been managing at your time there. And offline we can also discuss more on that, because this is where the region is going. So if you maybe you've seen a lot of interest now from Saudi Arabia with their cloud seeding program started recently again. There's also unofficial news with other countries that are also expressing interest here in the region. So I see a very strong need for such cooperation and a proper framework for it, similar to what you have experienced with the council. So the next question is, what are some of the key research questions we should be currently working to address in order to better mitigate climate change impacts on water resources? And maybe specifically putting it in the context of the Arabian Peninsula. It's one of the hotspots we always see, the most vulnerable to the rising temperatures.
Yeah, no, this is it's a great but also a loaded question, right? There's a lot of moving parts to this. I think that there are a number. I'll just briefly highlight sort of the vulnerability of the region to climate change, and then talk about the role of cloud seeding or potential weather modification for the peninsula, Arabian Peninsula, and that, which is extreme heat. I mean, this is an issue that's going to affect globally, but I think the Middle East, and particularly the Arabian Peninsula, is extremely vulnerable to that. That's where you're going to see one of the, literally, no pun intended, hotspots in terms of incidence of extreme heat. It's just one of those areas that's naturally prone. Sea level rise as warming increases, encroachment into land, and then drought issues being even more exacerbated. In fact, the region has been very acutely impacted in terms of water supply availability, because for most of the Arabian Peninsula and the GCC countries, there is no surface water supply system. For the most part, there is almost no surface water supply system that naturally occurs in the region. It's groundwater, which has been historically tapped because of the absence of surface water supplies. And then now, through the use of desalination, incorporation of treated seawater to supplement water supplies for the region. I think all the GCC countries are largely dependent. I mean, significant amounts of their portfolios, up to 75%, is coming from desalination. So the question then becomes, what role can weather modification or cloud seeding play in this region that can help address that? Well, we talked about it up front. It truly is a water augmentation strategy, and desalination you can really view as a water augmentation strategy. It's bringing in a non-conventional source of water to supplement your existing water supply portfolio. Cloud seeding can do the same, and I would take it a step further, not just having cloud seeding efforts just to produce more precipitation in general, but I think there's an added benefit of the precipitation that's generated to also boost your other potential water supply source, which is groundwater. In this case, I don't know how you'd say if it's naturally or artificially recharged, because it's precipitation that's boosted through artificial means, but beyond just precipitation events as they occur to increase the natural soil moisture of the region, which then also, more clouds, more precipitation also, at least, I wouldn't say momentarily, but briefly reduces the experienced temperature. Now, there's added humidity, which is another issue, but that also actually is one of the prime conditions that makes cloud seeding in the GCC viable, because now you actually have natural, abundant amount of moisture in the atmosphere that you can utilize. But I would say cloud seeding has the role of not just increasing natural precipitation, but increasing natural precipitation for the purpose of boosting groundwater supplies, which is rapidly depleting and can then can increase the viability of that supply source beyond just relying purely on desalination.
No, indeed. And you also mentioned the issue of cost, of course. So I think the number you mentioned was an order of magnitude at least less in terms of comparison between cloud seeding and decel. I think that's pretty conservative. So
Yeah,
depending on the scale, I think we
yeah.
can. I've seen some stronger numbers. Yeah.
Yeah, yeah, and we can talk about it just to throw it
Yeah.
out so people have a perspective. And these are U.S. based numbers, so obviously
Yeah. Of
things
course.
may adjust depending where you are. So in the U.S., the numbers have been thrown out for desalination in terms of acre feet, which is the volume we use for water supply usage here, is desalination on average can cost about $200 per acre foot.
Mhm.
And just to give people perspective, an acre foot of water is the amount of water that is necessary to supply the needs of two medium-sized families for 1 year. Okay, that's 1 acre foot. So $200 per acre foot is the cost of desal water. When you look at the estimates for weather modification, it tends to range around $35 to $50 per acre foot. So quite a huge difference. But then you got to also understand the differences and potential limitations. You can scale up desal. I mean, it all comes down to cost, but in terms of weather mod, you have actual limitations because of your seeding particular storms, conditions can occur. So modest number, but also the scale differs, but still significantly cheaper than desalination.
Right. The last question I have here is, of course, we know that MEI is hosting a 4-day Climate Week virtual conference with some very interesting sessions I got a sneak peek into. So I was wondering if you'd like to tell us more about it. And it's going to be tailored, of course, to the MENA region in terms of geographic, the socioeconomic context, within, of course, the important topic of climate change. So if you can tell our audience more and they can attend next week, that would be great.
Yeah, Yusuf, I appreciate a good plug. So I thank you for giving me the opportunity to just mention this. So that's correct. So next week, Middle East Institute, and specifically my program, the Middle East Institute, which is the Climate and Water Program, is hosting an annual event, which is called MEI Climate Week. And so we started it last year for the first time, and this is the second time doing it. And essentially, it's a number of panels over several days. So June 6th to June 9th. June 6th, we'll be starting with a keynote address. And this actually coincides with UN World Environment Day, which actually occurs on June 5th. It's a holiday here in the US. It's a Sunday or weekend. So we're starting it the following day, and we're going to have a keynote address from the Minister of Environment and Climate for the state of Qatar to kick that off. The next 3 days focus on 3 different panels that cover different aspects I think are going to be interesting to folks that include experts from across the field and the MENA region. On Tuesday, we have a panel focused on the resilience, on local-led adaptation, the resilience of, or the future of resilient cities. And so we'll be talking about how climate change impacts really the urban areas of the MENA region and what are some of the efforts in place to make those urban environments more resilient, robust, in some cases sustainable. The second panel on Wednesday, which I'll actually be moderating, is on disaster preparedness and touches on some of the things we talked about, which is these climate impacts that affect the region in terms of sea level rise, warming. We haven't even really talked about extreme weather events, which, UAE actually experiences some of that, primarily Oman in terms of cyclonic activity. So all of these really extreme types of impacts, how can the region best prepare for that? What are some of the mechanisms in place? I'm sure cloud seeding will pop up there in some form or fashion, or at least I'll try to seed it, no pun intended, in the questions. And then on the final day, which is Thursday, the final panel is looking at the state or the current state of climate activism, primarily in the MENA region. And so what's the role of youth, civil society in terms of helping move the climate agenda forward in terms of achieving a more climate resilient future for the region and the role they can play in doing that. So each panel focuses on a different aspect of climate change, mitigation, adaptation, resilience, and activism. And so feel free to, our watchers, you can if you head over to mei.edu, the events page should have that posted, if not today, by tomorrow, this upcoming week. And feel free to access the event page and register, and you'll be able to view those panels and events.
Fantastic. All right. Well, thank you once again, Dr. Mohammed, for giving the presentation and, of course, sharing the insights and for the questions we had. The webinar is recorded, so it will be available on our website for those who missed the live stream. I encourage you all to attend our next webinar, which we'll advertise on our channels soon enough. Have a nice rest of your day, evening, everyone. Till next time. Thank you.